Welcome back to the deep dive. You know, we often talk about renewables, but what happens when the sun's not out or the wind just stops? Yeah, keeping the lights on reliably is a huge challenge. So today we're diving into something called compressed air energy storage, CAES. It's maybe a bit overlooked, but potentially really important. Okay, let's unpack this.
Yeah, what's fascinating here is, well, it sounds complex, compressed air energy storage, but the basic idea, it's surprisingly simple, and it's a serious contender for large-scale storage. Our goal today is just to pull out the key stuff, give you the real picture of where it fits in.
Okay, so simple concept, you say. Like, how simple are we talking?
Yeah.
Is it really just storing air?
Pretty much. Imagine you've got extra electricity, maybe overnight from wind turbines.
Okay, yeah, when demand is low.
Exactly. So you use that spare power to run huge compressors. They basically just squeeze air really hard, and then you store that high-pressure air, often underground, like in big salt caverns or old gas fields.
Underground, why there?
Well, you need huge volumes, and these geological formations are naturally sealed and strong enough to handle the pressure. Then later, when everyone needs power peak demand, you let that compressed air out.
And it spins a turbine.
Yep. It expands really fast, drives a turbine, and generates electricity. Simple physics, really, just on a massive scale.
Right, and this isn't just theory. There are actual plants.
Yeah.
Right? Like that one in Germany, Huntorf.
That's the one. Huntorf, been running since 1978, 290 megawatts. It proved the concept worked commercially using salt caverns.
Wow, since 78. So it's not exactly new tech.
Not at all. And then there's McIntosh in Alabama, USA from 91. That one was a bit more advanced.
How so? What did they improve?
Well, Huntorf had, let's say, efficiency challenges. McIntosh started integrating natural gas to reheat the air before it expanded. That boosted the output quite a bit.
Ah, okay. So they were already tweaking the efficiency back then. Why does that matter for, us?
Yeah, exactly. And this evolution, it really matters to, well, to you listening, your power bill, grid reliability, because CAES acts like this giant shock absorber for the grid. It helps smooth out the peaks and valleys in demand.
So we can help prevent those sudden price spikes we sometimes see.
Potentially, yes.
Yeah.
By providing power during peak times, it reduces reliance on expensive peaker plants. More stability, maybe fewer nasty surprises on your bill.
And it's huge for renewables, right? That whole intermittency problem. Wind doesn't always blow, sun doesn't always shine.
Precisely. CAS can store that excess wind or solar energy and feed it back when needed. Makes renewables much more reliable grid contributors.
Okay, that's a big plus. What else? You mentioned lifespan.
Yeah, that's another key advantage. These things are built to last. We're talking 20, 30, even 40 years or more.
Wow, compared to batteries.
Exactly. Much longer than typical large-scale batteries. And they don't really degrade much sitting there, low self-discharge, and they can handle lots of charge-discharge cycles.
Okay, durable and helps renewables. Sounds good, but there must be downsides.
Oh, definitely. But yeah, it's not all perfect. There are challenges. The biggest one, geography.
Geography? How so?
Yeah, you need those specific underground geological spots like the salt caverns or aquifers we mentioned. They aren't everywhere.
Ah, so you can't just decide to build one in any old place.
Nope. Location, location, location is critical. That really limits where you can deploy this technology effectively.
And I bet they're not cheap to build. The upfront cost.
Definitely not. The initial capital cost, the CapEx, is pretty significant. You're talking major construction, specialized equipment, potentially drilling, a big investment.
Okay, big investment, location dependent. What else?
Efficiency and energy density.
Yeah.
Compared to, say, lithium-ion batteries.
How does it stack up there?
Well, traditional CS, the round-trip efficiency is, okay, not amazing. Maybe 42 to 53%.
Ooh, compared to batteries at what, 85, 90%?
Right. So you lose more energy in the process. And density. Think about your phone battery. Tiny. Right. To store that same amount of energy with compressed air, you'd need like 9 times the weight in air. It just takes up a huge amount of space.
Which is why you need those giant underground caverns.
Exactly. Space is a big factor. You need scale.
Okay, so challenges exist. But things are evolving, right? What's next for CES? Is it getting better?
Yeah, this is where it gets really interesting. They're working on improving that efficiency issue. One big thing is called adiabatic CES, or ACES.
Adiabatic. What does that mean in simple terms?
Basically, when you compress air, it gets hot, right? Traditional CES often just lets that heat escape, waste energy.
Okay.
ACS captures that heat, stores it separately, and then uses it to reheat the air when it's released later.
Yep.
It makes a huge difference to efficiency.
How much difference?
Well, some reports suggest ACS could get up to like 83% round-trip efficiency, much closer to batteries.
Wow, okay, that's a big jump, almost double, and less need for extra fuel.
Yeah, it's a major step. And it reduces or eliminates the need for that extra fuel like the natural gas used at Macintosh. Much cleaner. And it shows the core idea is sound, just needed refinement. Then there's some really cool, almost sci-fi stuff happening, like underwater CAES.
Underwater, how on earth does that work?
Yeah, projects like Barrowmar in the UK are looking at storing compressed air in big tanks on the seabed.
Seriously, why down there?
Well, it gets around needing specific land geology, for one, plus the pressure of the water above actually helps contain the compressed air. Pretty clever use of the environment.
Huh, that's definitely thinking outside the box. Or under the water, I guess. Any other directions?
There's also work on smaller, maybe modular CE systems, so maybe not everything needs to be giant cavern scale, could be more localized, flexible uses.
Okay, so bringing it all together,
Yeah.
we use our will it change everything index, the WICE score, to kind of rate these things. Where does CES land?
We gave CEs a WISE score of 42.5.
42.5. What did that tell us? Is that good, bad, middling?
Well, it shows its strengths are definitely in that long lifespan we talked about, potentially lower environmental impact compared to mining battery materials, and good operational costs once it's built and running.
Okay, the positives. Longevity, environmental aspects, running costs.
But the score also reflects those challenges. The lower energy density compared to batteries, the efficiency hurdles of older designs, and crucially, that dependence on having the right geology.
So strong in some areas, but limited by location and maybe still catching up on efficiency tech.
Exactly. It's a really solid, powerful solution where you can build it. It's not quite a change everything everywhere tech, hence the 42.5. Powerful niche, maybe growing with ACAES.
So what does this all mean? We've gone from, plants built back in the 70s to these advanced concepts, underwater storage, better efficiency. It really shows how something as basic as compressed air could still be a really big piece of the puzzle for a stable, renewable grid going forward.
Yeah, absolutely. And this raises an important question, I think. As we keep pushing for more renewables, needing more storage, how will innovations in these big, long-lasting storage types like advanced CCS really change the game? Not just the grid infrastructure itself, but, how reliable and accessible power is for all of us in the future. Something to watch.